Welcome to the NPTEL course on computer system optimizations for machine learning. This is the lecture 7. We will have a brief recap on whatever we discussed in the last lecture. Then we will see some further nuances of fully connected layer computation. And after that, we will introduce the nonlinear operations or nonlinear functions which are prevalent in all convolutional neural network, right? In the last class, we discussed flattening. Yeah, we took one quantitative example of flattening. There we saw that if we flatten the input feature map as well as the filter, then how does it look like? And then we discussed about the fully connected layers, right? So remember, in fully connected layer are not too much different than convolutional layers. You can think that that's the degenerate case. That's the very simple case of convolutional layer where the filter size is exactly same as the input image size. Then you can project the filter on the input image only once to generate one pixel per channel, per output channel, right? If we have m number of filters, then that will generate m number of output channels. So that's why you can see that here we have m number of filters that got translated into m channels in the output feature map, right? So since we have total n input feature map, that's why we have n number of output feature maps also. So for each input feature map, we will get one output feature map, correct? So that's all about fully connected layer. And then we also discussed like how the matrix multiplication actually happening. Like each of the row in the flattened filter will get multiplied with each of the column in the flattened input feature map n times, because we have n number of output feature map to obtain this n by m output matrix, which is like m is the number of channels in the output feature map. For each of the channel we just have one pixel because this is a fully connected layer, and then we have n of those things because we have n number of images, n number of input images. So each of the input image will be translated to one output feature map, correct? So we also discussed that there is no temporal locality. Temporal locality is nothing but reuse of data within a time frame in this particular implementation, right? Now, as you can see, that all these convolutional operations can be translated into matrix multiplication, right? So now remember, whenever we have this matrix multiplication, yeah, you can write a code for matrix multiplication, and then you can think that what's the big deal of computation for matrix multiplication. But see, whenever we are talking about convolutional neural network or any large ML models in general, we are not talking about matrices which are just dimension of 4 by 4 or something like that, right? We will see that the matrix dimension can be like huge. It can be like 2048 by 2048, or even larger, like 8192, like 8K by 8K. Let's say we have a matrix multiplication of two square matrices where both the square matrices have the dimension of 8K, 8K by 8K, right? It can easily happen. Like, I'm sure that you use all this ChatGPT and generative AI. We will also discuss in a later lecture. So whenever these LLM computations are happening, easily some matrix dimension can be 8192 by 8192, right? Now, let's say you have a matrix size of 8192 by 8192, or let's say 8K by 8K. I'm talking about matrix multiplication, right? So there are two matrices. Let's say each of them have the dimension of 8192 by 8192, and if each element of those matrices are represented by 32-bit floating point number, then each of the element will take 4 bytes, right? Now 8K by 8K, two matrices, each matrix is taking 4 bytes. If you do this calculation, you will see that 8K by 8K is like 64 into 10 to the power 6. That's 64 MB, right? Now 64 MB multiplied by 4 byte, that's like 256 MB. Now there are two matrices, 256 multiplied by 2, 512 MB, right? So almost 1 GB, right? Now if you think our computers, like usually the cache sizes are in terms of like KB is if some cache might be of size MBs, right? So usually the main memory is like in terms of GB, right? So what I'm trying to point out that whenever we have this matrix multiplication, whenever we are writing that matrix multiplication code, like if inputs are A and B, then we write C, which is the output Cij or Cik equals to Aij multiplied by Bjk. That's how we write the matrix multiplication code, right? But then these matrices might not fit onto the cache. So cache is the memory which is staying near the processor, right? So if it is not fitting into the cache, then I mean, how can we do the matrix multiplication, right? Because remember, from DRAM, from the main memory, first the data has to go to the cache, and from the cache only we can perform the operations. Anything, multiplication, addition, any operation has to be done when the data is in the cache, right? We cannot, it has to come to the cache. Now, the thing is, when we have a large matrix multiplication, and if it doesn't fit into the cache, then the matrix multiplication is tiled to fit into the cache. This tiling is a very important concept which is used in any modern day compiler or any modern day library. Okay. Then the computation is ordered to maximize the reuse of the data in cache. So for an example, let's say for the fully connected layer. So we were discussing about this fully connected layer, right? Now for this fully connected layers, we have the filter size of CHW by M, right? And then we had the input feature map of N by CHW, right? Or M by CHW and then CHW by N, right? Whichever notation you can think of. Now, if these matrices are actually not fitting into the cache, then instead of taking the whole matrix from the DRAM, we can actually take a tile of the matrix. So whenever we say tile, that means the matrix is segmented into multiple tiles, and then let's say those tiles can fit in the cache. Of course, if the matrix is segmented, then the size is less, and then there's a higher possibility that those tiles can fit onto the caches, right? So in this case, this filter says M by CSW has been segmented into 4 tiles where F00, F01, F10 and F11 are there. So similarly, this input feature map also has been divided into 4 tiles: I00, I01, I10, I11. Now we have to perform tile matrix multiplication, right? So this F00, so remember this F00 itself is a matrix, it's not just a number, right? We just divided the matrix into 4 quadrants or 4 tiles. This F00 will get multiplied by with I00, and then if we want to perform this matrix multiplication, then we have to do F00 I00 plus F01 I10 to get the first tile of the output feature map, right? Now here we need to maximize the reuse of the data in cache. So what we can do, so you can, if you see closely, you will see that we have this F00 I00 plus F01 I10, right? Sorry, let me go back just a moment. Yes, so we have this F00 I00 plus F01 I10. Now all these 4 values are different. So if we immediately want to compute this F01 I10, then we are not doing any reuse. But then if you look closely, the next tile is using F00 I01, right? Here we have F00 I00. Now we can reuse this F00 from the cache. So we have to do this careful reusing. So this is one way of reusing. Or we can say that, okay, I00 is already loaded, so let's see which other tile of the output feature map requires I00. This is the other tile, right? So we may not need to do all the multiplications at once, or sorry, all the tile computation in the output feature map at once. We can reorder the computation to maximize the reuse of the data in cache. So that's the main motivation of this data reuse. Again, so now we are actually going into the details of the computer system. So I mean, in any case, any way you do the multiplication, you will get the same output. But our goal is to get the same output in a effective manner. When we say in an effective manner, we mean in lower latency or lower memory accesses and all those things, right? So this is one trick which one can do to reduce the memory access or to reduce the latency of matrix multiplication. Okay, now this kind of operation or this kind of tiling is very popular in many of the state of the art library. So this matrix multiplication is usually known as generalized matrix multiplication GEM. For CPU, there are libraries like OpenBLAS, Intel MKL, etc. In GPU, there is QBLAS, QDNN, etc. All these libraries actually make use of this tiled matrix multiplication. So what these libraries will do is they will note the shape of the matrix multiplication and select the implantation optimized for that shape. So it will note down the shape of the matrix multiplication, and remember, the libraries already know the cache size or the memory hierarchy of the underlying hardware, which can be CPU or GPU. Now, from the shape of the matrix multiplication and from the knowledge of the memory hierarchy as well as the cache size, they can select like how to tile or how to reuse the data so that the computation latency will be less. Now, again, this optimization usually involves proper tiling to storage hierarchy. Now, this is a very important point, the storage hierarchy. So, different CPU has different storage hierarchy. Like some CPU might have just L1, L2, some CPU can have L1, L2, L3, etc., etc. So, depending on different storage hierarchy, the tiling can be different. The pattern of reuse can be different. We will again come back to this tiling when we talk about accelerator, but this is one preliminary introduction of tiling. Hopefully you understand that like one simple trick can actually minimize the latency in a huge way. We will probably see some quantitative example at some later point of time. Now, I'm sure all of you know about this TPU. These TPUs are nothing but tensor processing unit. So GV100 is one tensor core. Now this tensor core can do multiply and accumulate operation. It will take two matrices or rather three matrices. The first two matrices will be multiplied. So let's say this is A and this is B, then this is C. So they are doing D equals to A multiplied by B plus C. Now each of these A and A, B, C matrices are 4 by 4 matrix, right? So they have new opcode. This tensor core introduced a new opcode called matrix multiply and accumulate, right? So remember, opcodes are nothing but the lowest form of instructions. Like if we say add R3 R1 R2, that means R3 equals to R1 plus R2 in our RISC processors, right? So they introduced this tensor code introduced a new opcode called matrix multiply and accumulate. That means this opcode will take three input A, B, C, and then it will perform A, B multiplied by C, which is nothing but this D, which is nothing but the output. Okay. Now they also introduced this matrix multiply accumulate for FP16 operand. So each of the entry in this matrix multiplication in all these matrices are 16-bit floating point numbers, right? Now, as you can see, we have three 4 by 4 matrices, so that's why there are 48 inputs, and then the output will also be of size 4 by 4. So there are total 16 outputs, right? And then in total there are 64 multiplication operation, 64 addition operation, which I mean you can easily get this number if you just work this example, like example of two 4 by 4 matrix multiplication plus the product. If the product gets added with another 4 by 4 matrix, then you will see that there are total 64 multiplication and then 64 addition. So in total, this particular tensor core has the throughput of 120 teraflops per second, which is really high. Teraflop means, I mean, flop stands for floating point operations. Okay, and then the performance per watt is 400 gigaflops per watt, means in by consuming 1 watt of power, it can have, or it can perform 400 giga floating point operations. Okay, which is quite impressive. So the main motivation behind showing this tensor core, or showing this kind of slide, is to let you know that we are doing the same matrix multiplication, but then in hardware, in computer system, there are different optimization which will make this matrix multiplication faster. Okay, now this is the slide where I am showing you the overall structure of tensor processing unit. I mean, I am not going into the detail. So this is the top level architecture. So this particular architecture is the top level architecture of the tensor processing unit. Okay, again, tensor processing unit is nothing but there is some matrix multiplication followed by accumulation is happening. That's the excerpts of the tensor processing unit, right? So it has multiple things, like it has some interface of PCIe, there is a host interface, then unified buffer, then some setup is there for systolic data, some weight FIFO accumulators, everything is there. But the main unit is this matrix multiply unit. So where these weights are coming from this side and the data is coming from this side. So finally the data is, so there is a specific data flow. So data is flowing this side horizontally as well as vertically. The partial sums are um, flowing vertically, and then finally they are accumulated to get the final output. When we will discuss about systolic array, we will see more about it, but the core of this tensor processing unit is nothing but matrix multiply unit. Okay, now to get this matrix multiplication unit working, we have all the peripheral component like weight FIFO, this setup, some buffer, then some accumulators, activations, etc. Then there is some control logic also, correct? So you can see that there is some specific flow of control. Now that's the TPU for you. But again, the heart of TPU, the core of TPU is nothing but matrix multiplication unit. Okay. Now finally, let's see different nonlinear functions. So far we have discussed about convolutional operation, then we have discussed about fully connected layers. Now we will discuss about nonlinear operations. So if you remember the whole picture of convolutional neural network, there are convolutional layers followed by this nonlinear operation, right? Now, why do we need nonlinear operation? I think we discussed in the very first or second lecture. If we don't have nonlinear operation, then all those convolutional layer can be collapsed into just one layer, which we don't want, right? Because if they are just collapsed into one layer, then we will not get the different high level as well as low level features. So that's why we have different nonlinear operations. So there are many nonlinear operations. So sigmoid is one of the popular nonlinear operation where y is equal to 1 over 1 plus e to the power minus x. X is nothing but the input. So you get a row of one row of value and then you just apply this function y is equal to 1 over 1 plus e to the power minus x. So that's one particular nonlinear operation. Then we have hyperbolic tangent e to the power x minus e to the power minus x over e to the power x plus e to the power minus. That's another nonlinear operation, right? So similarly, there is rectified linear unit. In short, it is known as ReLU. ReLU is nothing but y is equal to maximum of 0 comma x. There is leaky ReLU, which is more smooth than ReLU. Then there is something called exponential LU, which is again smoother than leaky ReLU as well as rectified linear unit. So there are all these activation functions are nonlinear functions. Now different nonlinear function has like different effect on how the training happens or how the inference happened. Since this course doesn't have the scope of going into details of the theory, I would like suggest go to the original paper which suggested or which proposes ReLU or the leaky ReLU or the sigmoid to see why do we have different nonlinear activation. In this course, we will only limit the discussion for the computation, like what's the function, what's the computation, that's all. Now, apart from ReLU or sigmoid or those nonlinear operation, there is one very useful or commonly used nonlinear operation is pooling. In short, they call they are called as pool layer. Okay. Now this particular pool layer or pooling operation is performed to reduce the resolution of each channel independently. Okay, now it can be overlapping or non-overlapping, depends on stride, like convolutional layer. Now this pooling layer or pooling operation increases translational variances and noise resilience. So we will see how it increases translational invariance and noise resilience. How does it do that? How does it increase the translational invariance and noise resilience? We will see very soon, but first discuss what's pooling. Okay. Now let's say we have this 4 by 4 input image, and then we want to perform a 2 by 2 pooling with a stride length of 2. Okay. Now again, there is some similarity with respect to convolutional operation. So whenever we perform this 2 by 2 pooling, first we have to take this 2 by 2 patch. These are the exact pixel values 23, 7, 10, 1. Now there are two kind of pooling. One is max pooling and another is average pooling. For the max pooling, we just take the maximum of this value. So maximum of all these four values is 23, and we put this value in the output feature map. Right? If we have the average pooling, then instead of taking the maximum, we'll take average of all these four numbers and we'll put the average value in the output feature map. So that's the max pooling, and that's the difference between max pooling and average pooling. Now that's the first patch, right? We have a 2 by 2 pooling. So remember, pooling doesn't have any weight involved. You just need to mention the size of the pooling window, right? So since we have a 2 by 2 pooling, we took this particular window. Now we told that stride length is 2. If the stride length was 1, then the next window would have been this. But since our stride length is 2, the next window is this one, where we have this 7890. If we have the max pooling, then the maximum value is 9, which is put in the output feature map. If we have the average pooling, then the average value is 6, which is put into the uh, output feature map, right? So that's pooling. I mean, very simple, similar to convolution. There is no weights involved. The concept is very similar to convolution, where we need to get the image patch by patch. Now in case of pooling, we just need to specify the pooling window. Now we have to get that particular patch of the input image, and then depending on the max pooling or the average pooling, we just operate on the pixel values in that particular patch. In case of max pooling, we take the maximum value of all those pixels in the input feature map. In case of average pooling, we take the average values of all the pixels in the input feature map, all the pixels in that particular patch of the input feature map. So that is pooling. Now, as I told, that pooling increases translational invariance and noise resilience. So let's see how pooling involves in noise resilience first. Oh no, sorry. Before noise resilience, let's see how it captures this translational invariance. Right. So remember, when we say translational invariance, we mean that, let's say we have one image. Let's say 27 by 27 image. Now let's say the task is the recognition task. We have to recognize which animal is there in the image, right? Now if there is a cat in the top right corner of the image, versus if there is a cat in the middle portion of the image, both the image should be classified as cat, right? Now there is actually no difference in those two images, but the difference is only in in terms of where the actual part or actual pixels are in the images the cat was there. Now if we just shift that image, that cat image, horizontally or vertically, it should still recognized as cat. It should still be recognized as cat, right? Now this property is called translational invariance. So for an example, let's say this is first case, where you can see the image is probably 1 2 3 4. This is a 7 by 7 image, right? And then we have a letter C. So this is the letter C in that 7 by 7 image. And then let's say you need to develop a neural network which just recognizes this particular image, right? Or this particular letter, right? Now it will recognize as the letter C. But then let's say this letter C, these particular pixels are shifted downwards by just one row. Now the letter is still the same, right? But the position of the pixel got changed. So it got translated, right? Now in this case, pooling actually comes into the picture. Now let's say we perform a convolution operation with a filter size of, let's say, 4 by 4, and this is the patch. This is the first patch we will get. Like if we take 4 by 4, then this is the first patch we will get. Let's also assume that these are just represented as the binary number. If there is a pixel or if there is some value, then it is 1, otherwise it is 0. So that's why you can see that in the periphery, in the border, we have all these 1. So that's the letter C. Now if we perform the convolutional operation on this 4 by 4 patch, then we will get one output of the convolutional layer, and let's say there is no pooling. So let's say our DNN just say, or the classifier layer just say that if there is a like pixel at the top left corner, then it's C. Let's say that's the recognition. That's how the recognition happens. The image classification happens. Now in the second case, the same image, that same C is actually shifted downwards, correct? Now if we perform a convolutional filter of size 4 by 4, if we perform the convolution, then we will get the same patch in the second row. No longer, we will not get in the first row. So if our recognition or the final layer which is doing the final classification is trained in such a way that it says if we have a pixel in the top left corner, then only it will be recognized as C, then this particular case will not be recognized as C, and that's where the pooling comes into the picture. Now in this case, if we perform a 2 by 2 pooling with a stride length of 2, then we will get this value, because remember, we'll take the max. Let's say we are doing the max pooling. Yeah, it is already written max pooling. Then we will take this particular patch, take the max value and put it here, and then all those values will be 0. In this case also, we'll take this 2 by 2 patch, and then we'll get the same pixel value at exactly the same patch or exactly at the same position. So that means the output feature maps are similar. Now why the output feature maps are similar? Because we applied this max pooling. Now since these output feature maps are similar, it will be recognized as, or there's a higher chance that it will be recognized as the same letter C. So that's the main goal, or that's the main advantage of max pooling, right? Now I also told that this is max pooling helps in noise resilience. So let's say again we can take the same image C. This is probably, let's say this is the cleanest image, and for like sake of argument, let's say they are no longer denoted as the binary values, but let's say they are denoted as the pixel intensity. Now let's assume that our neural network trained with these clean images, but then when you actually test the image, then, or when you actually get the image, then let's say we don't have the pixel in these places, or sorry, the same pixels are there in these places, but then there are some noise values in all these places. Now if that is the case, then we'll have some noise values here. Now usually the noise values, the intensity of noise pixels are lesser than the intensity of the input pixel. Okay, so if we perform the max pooling, then we will see that it will be nothing like this maximum of all these values, so the noise will be suppressed. So we'll get the exact same value. So that's how this max pooling helps to prevent noises, or helps in resiliency, helps to increase the resilience with respect to noise. Now this is one better example of translational invariance, where it provides the same output independent of the location of the object within the image. Let's say we have three images, where we have this image of this idol or the doll, but in these three different images, the actual image or the actual portion of the interest is actually shifted, right? is that's the translational. That's a. I mean, it has been translated. Now we want all these images to be classified as the same label or the same class, right? So pooling actually helps to classify these all these images as the same class, and that means pooling helps in translational invariance, or pooling keeps this translational invariance property intact. Okay. So that's the end of this lecture. Thank you very much. In the next one, we will see some more convolutional layer or some more functions in the convolutional layer, and then we will see some compute property of this convolutional neural network. Thank you very much.